There we go. So to all of you people who is not here, I have to talk to the camera for once. We that's left here have decided exam 22nd of May or 26th, maybe even 27th Saturday. They have exams on Saturdays as well. So in this period, these 3 days, we start as a suggestion at least. So if you have any strong feelings about it, anything with collisions there, then reply as soon as possible. And then finally, when we have one date that we all can agree on, I will send it into the administration, and hopefully then we will be heard. That's not necessarily the case, but you never know. Okay, we just discussed the exam date. Do you have any preferences? If
it's before the 10th June, I think it's
yeah, no, we had a couple of suggestions for dates. May 22nd, May 26th, May 27th, one of these three for now. That's okay for you? Yeah. Okay. Last time we finished with multigrid. So the topic today, within fast solvers, Krylov methods, conjugate gradient. And tomorrow then we will start with finite volume unstructured mesh systems. I'll put out some more material for you, so you can have something to prepare if you like. Now multigrid, if I recall correctly, this conjugate gradient, it's something that a student wrote. So he reads conjugate gradient made painless. So he's trying to sort of give a simple explanation what is conjugate gradient, and he's done a fairly decent job. So I've stolen some of the examples, figures that he has. So this is actually a very nice place to start with as a reading of the theory behind conjugate gradient. What we then are going to go through is sort of an excerpt from that, starting here. It's just handwritten, but hopefully it should be readable. So we have our problem that reads, should be here somewhere, but it is not. You have a linear equation system. You have a matrix A, big one, and then your unknown x's, and then you have the right hand side equals b. Solve it fast. With the Krylov methods, we change sort of the way of thinking. We don't look at the function or the equation system directly. We look at something called a functional, a quadratic form. So we construct a function looking something like this. A being our coefficient matrix, x vector, that's our unknowns, and b, that was the right hand side of our equation system. C here is just an arbitrary constant. And instead of solving our equation system directly, we look at this functional and seek where he has a extremal value, meaning all the derivatives for this guy equal to 0, meaning something like this. So wherever he is 0, then we have an extremal value. Now what's so good about that? Well, if you take the derivative of that function, it actually can be shown that the derivative of this strange little function that we had becomes our equation system, meaning when you have found the place where all these gradients are 0, then you have actually a solution to the equation system. So that is sort of a change of thinking. Instead of solving an equation system either directly or indirectly or whatever, you are seeking out places where you have a minimum value of a function. So of course this can be done in many ways. Let's get rid of these. I think I had something here. Yeah, it's just a visualization. So let's just try to run it and see what happens. So I have here just constructed, say, a terrain. So you have only a two-dimensional problem actually, x and y if you like, and I just constructed a function, arbitrary, but it has several local maximum, minimum, and then how to find them. So you can sort of think of it as unknown terrain. You have no idea what the terrain looks like. So then you just talk to the army, you hire a plane and throw out some paratroopers, give each of the guys a GPS, and then when they land in this unknown terrain, it's dense fog, so they had no idea what this terrain looks like. So they just start walking, and they are instructed, all the soldiers are instructed to walk upwards, always upwards. And when they can't walk any higher, you are at the peak, and then they just report in position and altitude. And to be sure that you have covered the entire domain, okay, then you need a lot of them. And here the initial positions are just random. And as you can see, from starting points, the green ones, to a stop point, they sort of agreed finding the different peaks in your terrain. So this actually is sort of an optimization technique. It's widely used. One might argue that shouldn't it be better to use sort of a structured initial search pattern here instead of using random? Yeah, maybe, maybe not. Not so easy always finding out what is most efficient, but random is widely used actually. We are not going into the details here in optimization, but let's see if it's possible here to flip it. I mean, optimization, that is a topic of its own. So yes, they find all the peaks, so not a problem if you have enough of them. And to be dead certain that you have found the biggest one, you see for yourself, well then, depending on the terrain of course, you're going to need a lot of trial and errors here. Not so necessarily so easy. But the idea is fairly simple, just walk upwards. Or, as we are going to do, flip it upside down and walk downwards. We are going to look at local minima. We are minimalizing a function. So what we are seeking, where is all the derivatives, everybody equal to 0. That is what we are seeking. Now, as as always, I must almost say, we define the residual to be sort of the offset. Now remember, residual here being a vector, and okay, if all of the terms in this vector is 0, okay, you have found a solution. Luckily for us, with these numerical systems, the terrain that we are searching is not going to be so bumpy. You will have one single minima that will then be our solution. You might find the equation systems where you have more than one solution, but normally you will only have one. So it shouldn't be a problem. As soon as if you have one solution, then it should be the one and only solution, at least for most practical problems. So what's nice with our logic now, find wherever all the gradients are 0. And also, if you look at the residual, that's actually now directly the negative gradient. So when you are deciding to sort of finding your search direction, where should you go? Well, you go in the gradient direction. And if he's 0, then you don't have to walk any further, then you have the solution. So he will automatically now give you the direction where you should go. So if you have, say, one initial starting point, one arbitrary x, okay, you can calculate your residual. When you have the residual, then you know which direction to go to find a better x closer to where everything is 0. That's the philosophy. It's actually possible to prove it, but a little bit tedious math, so we won't go through all this. So yes, we are seeking a minimum where our function f as minimum, where all the derivatives are 0. So the first try, the method of steepest descent. So now you have to think like these paratroopers that had the job finding the terrain, but we have to think sort of in the other way around. You are up on the mountain and you have to go down to the valley, down to the bottom of the valley. Where do you go? What's the fastest way down? Well, one way to think, sort of, you don't look at the entire terrain, sadly, or else you could have planned the entire course, the optimum course. Here we just say, find wherever it is steepest and always walk in the steepest direction. That should be the fastest way down from the mountain. It's not true, but sort of a first initial guess, why not? At least you go down, it should work. And yes, it works, but it's not so efficient. But it's very, very easy to set up. So our new position will be based on the initial position where we were standing, and then we walk in the residual direction. How far should we walk? How big step should we take in that direction? Well, that of course now depends on the terrain, but we should take one step as long as you go down. If you take a giant leap, then you jump across the entire valley. That's no good. So as long as you are still going down, we accept this new direction. So the alpha has to be calculated until the derivative in now this new direction we are going in is 0. Then you know you are from going down starting to go up again. So you calculate alpha this way. So possible here to calculate it, but it takes a little math to do it. But the final expression for it, fairly neat and simple. So you have to do some matrix operations, of course, after finding the residual. some multiplications, but absolutely possible to find it. So the entire algorithm, that's 3 lines. Well, and then a for loop outside it. Start wherever you want. Calculate the residual. Use the residual as a new walking direction. Calculate alpha to find out how big should your step be. And then you just update. And then you do it over and over and over again. So that is the idea. So let's try it. Here we have an example, and I believe it is the same example as you find in this where was it? Conjugate gradient. Here it was. So this is actually our problem now. You have 2 equations, 2 unknowns. So of course nothing to use heavy methods on. You can calculate the answer directly. You can here draw it graphically. You have the intersection between these 2 lines, so we have the solution at this point. That's the point we are seeking. So now you have to imagine, for 2-dimensional problems, not a big deal. 2 equations, 2 unknowns. As soon as you go to 3 or more, you can't draw it anymore. It's not possible. Hence we are using 2 by 2 as a visualization, nothing more than that. So you have to imagine an n-dimensional space, which is not so easy, of course. But for this problem, you can now actually calculate all these strange expressions, all the vectors, all the arrays or whatever. And here I have made a contour plot of the entire functional, the f function that we are seeking to minimize. We know the solution somewhere here. What was it? 2 and minus 2 or something like that. And here I have started same initial point as the one you find in this conjugate gradient made painless. Now in the starting point you first calculate the local gradient here, so you get the direction, the way you are going to walk, and we are walking downwards. So you find the direction, and then you look in that direction all the way until you start to go up again, and then you find the next point. So the philosophy there is very, very easy, of course. One giant leap down here. Then you have to do the same here. Find the local gradient and determine, okay, how big should my step be? So we go all the way down here, and then you continue. Now we don't have enough easel lines here, but you see what's going on. So it's not the smartest algorithm. If this terrain of ours, if it had been sort of a narrow canyon, you would be in trouble. If it were circular, this would have been a very good idea. Sadly, these functional in practice, they are going to appear extremely narrow and long. Yes, they are actually canyons, which means sort of imagine you are seeking your way down, blindfolded, walking in a narrow canyon. You are walking bang, 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 bang all the time, smashing your head against the walls. And you see also, he has used the same direction many, many times, over and over again. So this must be possible to do more clever. So this steepest descent method, it belongs together with, say, Jacobi Gauss-Seidel iterations. So I don't know how many I need to take, 25 or something, before this algorithm terminated. And now he tries again. Initial point, first leap, but then he's going to take forever actually to find the bottom point, and so on. So no, it's not the brightest algorithm, but it's fairly easy to program it. Let's see where we do. Yeah, I have the calculation for you somewhere. I have not programmed this one as a steepest descent method in practice because I wanted to visualize it. You have another code later on. But the philosophy, fairly simple, and yes, it works. You can do this many times, but it's not super efficient. So as it says here, you go back and forth in the narrow valley. So you use the same walking directions over and over again, which then obviously is inefficient. If you have one direction, then you shouldn't use that direction more than once actually. So what we are now going to do is sort of flip space a little bit. When you take this this f contours, the function, and redefine space so that these would be perfect circles. If we could do that, then you see what happens when from the first step, finding here the point where you start to go up again, then during the next step you will hit bullseye every time. So if we could sort of fold space, change space a little bit so that whatever terrain we have, this narrow canyon, could be circles, then we would be very happy indeed. And that's actually the basis behind conjugate gradient. So now we are walking, it's what's called the conjugate directions. So here we have the our equation system, our functional to be minimized, and the steepest descent. Fairly easy logic behind it, but sadly, no, it's not so efficient. So it was not the best. Yeah, I have here just an example how to use it on a Poisson equation, finding the equation system. Now normally, remember with this A matrix, that's the coefficient matrix, you never store the entire A matrix. You are going to kill yourself, or kill your computer at least, if you try to do it on a big problem. And also the A matrix, they only consists of coefficients like -2 over delta x square, 1 over delta x square. That's all you find inside a matrix. Okay, these numbers can change, of course, if delta x varies, if you don't have a uniform mesh, but still you don't store an entire matrix. That would be silly. Also, most of it is going to be 0 anyway. So here the residual is now calculated based on finite difference from a Poisson equation, as you should recognize. So yes, quite possible. You're going to find or use here some dot products and finding an update for your new guess. Here he has used F. That shouldn't be so wise. Should be X or something. Would be better. Yeah, never mind. So what's bad so far? Steepest descent, using the same directions over and over and over again. So it takes forever actually to find a solution. So instead of just walking straight down, we are now talking orthogonal directions, which is sort of a math concept. We have the definition for it later. But what's then going to happen, hopefully, is that the space here, sort of being an elongated valley, will actually now look something like this, perfect circles. So vectors up here that sort of have a very strange angle between them will actually be orthogonal in this space. So we have to sort of translate the 90 degree here to whatever degree we are in practice going to use up here. And to find that one, yeah, he's even tried to draw it in 3D. It's getting rather messy. And if you think in n dimension, you're going to be really confused. So easier here. You have the two vectors. They will be orthogonal here, based on, of course, our coefficient matrix A, if this matrix product equal to 0. So yes, it's fairly easy to calculate it. The philosophy behind this, not so easy. So you can have a peek if you want, but this will be now the heart of our algorithm actually. So it's fairly vital. So now we are going to go in the conjugate directions. So here you now have conjugate gradient. So same setup for the problem, linear equation system, minimize this functional. So to start the algorithm, we have no choice than do as we did with the steepest descent. That's the first step. So we have no choice there. But the next one, the next search directions, will then be an update. So, well, actually it's easier to see it for the entire algorithm here. So the first one we do as we did with the steepest descent, not a problem there. And then we now have to seek out our orthogonal directions, finding updates. And you see the program is now not 3 lines, but it's 5. So it's still extreme compact codes, not much programming required. However, what is required is all these matrix products. And yes, we are going to need some representation of this matrix A inside your algorithm somehow. We'll see later how this can be done without blowing the memory totally. So let's have a peek how this one can look like. The same problem. And we have the same initial point. So now we have, as before, starting point, find the gradient, take one step as long as you go down. And now we are seeking the orthogonal direction, not perpendicular. Then we ended up, where was it? Somewhere here. So now we use the orthogonal direction and we hit bullseye directly. 2 steps, you have the solution. You can do it over and over again, and he always hits bullseye every time in only 2 steps. Doesn't matter where you start. So this looks very nice when you have 2 equations and 2 unknowns, of course. So in real life, no, you don't hit the bullseye, say, with a given number of operations. It's still an iterative technique. So it's not all that beautiful, although for now it looks very promising indeed. So steepest descent was very bad, balancing Jacobi Gauss-Seidel. Conjugate gradient alone, the sort of the base algorithm, he should balance an SOR with an optimum omega, and even better. And also the code 5 lines. So it's very, very easy to program. So here we now have a whole bunch of different conjugate gradient algorithms that has been developed. But these are not just conjugate gradient. They are conjugate gradient with something extra. Now we have to discuss this a little bit extra. These names, they're quite famous, and in many, many codes you will actually find the option here, choose a solver. Okay, then you find these names. B conjugate gradients, B conjugate gradient stabilized, squared, general minimum residual. You have plenty of these. I think these are the most famous. What really speeds up the solution process, that is what's called preconditioning. That is something you have to do in order to really make this conjugate gradient work, and work fast. And the philosophy, this is your original problem. We just modified a little bit. We try to make an improvement before we begin. And the improvement reads something like this. You have an M inverse matrix, multiply on each side. And this M inverse should now be, helping for solving this problem. You can see if you just switch this M with A, then you would have solved the problem directly. Then you would have A inverse multiplied with A. Okay, then you are left with the X. Then you have solved the problem. So if M inverse is as close as possible to A inverse, that would be beautiful. But then, of course, you have solved it directly. In practice, that would not be possible because the A matrix is then mostly zeros. The A inverse is going to be a full matrix. And that's the trick with storage in a computer. You store a matrix, but you only store the elements different from 0. So in the expressions that we have with matrices, we can use the A matrix in a computer program without storing all the zeros. So that's not a problem, actually. We can survive with a rather big coefficient matrix using this technique that is called sparse matrices. I'll show you later. But the inverse, A inverse, forget it. He's going to be full, and then for a big problem, you blow any memory. So here you sort of have to do your weighting. How well can you find this M inverse without blowing the memory, but still at least let this problem be easier to to solve than this one. So that is sort of the job for the preconditioner, and your choice how well you want to do this. How efficient should it be? That can be sort of the pain. So some examples: Jacobi preconditioning. That is something that is really not helpful almost at all. Very bad indeed. Very popular. An incomplete lower-upper preconditioning. So we'll have a look at this a little bit later as an example how this can be done. So and you have others as well, but it will typically depend on what choice you make of the different solvers. So so here for these 4 different ones, they typically have their own preferences. This method like this type of preconditioning, this method he likes another one, and so on. So what's most efficient? Depending a little bit on which version you want to use. We'll see some examples of it later on. Okay, any questions? Then we take a break.